Okay, can everyone see the aurora borealis?
Absolutely.
Beautiful. By the way, there was a giant outburst on November 4th, and it was incredible because we even had pictures of the aurora borealis that showed up on the Cape Cod Canal that was uploaded to spaceweather.com, as well as a number of, we had a number of reports from New Hampshire, Maine, Vermont, Wisconsin, Montana. So it really was a major outburst. So I'm going to just start my presentation here. So hopefully this will open up pretty smoothly. And is my voice coming across okay?
Yes, you're fine.
Okay, I just want to make sure before starting and assuming everyone's hearing me and no one's hearing me. Okay, here we go. And I'll just move my cover off to the side. Okay, welcome everyone, and I appreciate being invited to the Ethelbert Nature Club. We've done programs in the past where we've actually done a talk in person. Look forward to doing that, hopefully in 2022. Things will improve and get better, and hopefully that part will arrive for your projector in time for all that. But we do appreciate the invitation, and like Dave said, the Athol Library is home to the Library Telescope program here. So this is a talk about the cosmos, exoplanets, and what's going to do it for us. It's going to be the James Webb Space Telescope. And my title says, Seeing to the Beginning of Times. It's exactly what this giant telescope is going to do. Brand new technology and an infrared telescope that will see the first galaxies and the first stars forming. So it's really quite amazing. So once again, thank you everyone for inviting me. We do appreciate the efforts you put into organizing this. And without further ado, we'll start off with the process here. And I did mention the library telescope at the Athol Library. Anyone with a library card can take that out. So that's something to keep in mind. And by the way, probably at the end, I'm going to go over what is visible in the sky and open myself up to questions at the last slide. But you'll get all that information about current sky conditions in addition to what I'm about to talk about. So the history, understanding the need for a new telescope that will allow us to see all the things that Hubble, which is the major telescope up there, and Chandra, an X-ray telescope, cannot see. And one thing that you have to understand is that if you want to go back in time, everything is redshifted, which means going into the infrared. So this is the important thing. 30 years ago, Riccardo Giaccone, basically, he was the visionary director of the Space Telescope Science Institute. And he was one of those people that understood the need to get organized. And especially with the, this is prior to the launch of the Hubble Space Telescope. And once that got underway, he made sure there was he described an organization that would maintain all the data downput from all these places in space, these space telescopes, from Chandra to the brand new James Webb Space Telescope, to Spitzer, which has recently been retired. And all these are downloaded to this Space Science Institute, and they're managed there worldwide, so scientists can take advantage of this. So this is important to understand, because if you can't get the data in front of the people who need it, you're not really well organized. And there was some incidents early after Hubble got launched where actually the Hubble Space Telescope had blank spaces where no one was taking advantage of the telescope being there. So it was very important to go ahead with this organization here. And he called this systems engineering. And all the system engineering means central location, managing everything across the globe so we can take advantage of this premier telescope. And this is a picture of Riccardo. Now, 1996, that's as far back as this goes for this next generation space telescope. That's what they call it. This has been a long time in coming. James Webb, for those who are not familiar with him, he was the second administrator of NASA, and which was established in 1958. He basically managed NASA all the way to just prior to the official moon landings. till 1968. Was a tough time for NASA. If we remember back then, they were preparing to go to the moon, and the first astronauts that were on the spacecraft were ready to exercise all the systems. Actually had a major malfunction where there was a fire on the spacecraft, and it ended up in the loss of 3 astronaut lives right on the launch pad, which no one ever conceived. He got a lot of heat for that. He investigated it thoroughly, organized a response to that, and got NASA back on track just prior to the moon landings. So he was a very well respected administrator, very well organized, and made sure NASA got the funding it needed to succeed in going to the moon and beyond. So that being said, I want to start off everyone on an even keel. Sometimes as an astronomer or an amateur astronomer, I'm a retired physicist. You take too much under assumption basically and use the word light year very prolifically in all the talks. And I went through one talk one time when someone raised their hand at the end of the talk and said, by the way, what is a light year? So we're going to head that off right in the beginning. Light year, it's a unit of distance, okay? And it describes how far light travels in 1 year. And I did a little bit of math here. As you can see, light travels 186,000 miles per second, or 300,000 meters per second. 300,000 kilometers per second in 1 second. To give you an idea of how fast that is, one light beam released at one point on the Earth would circle the globe 7.5 times within 1 second. So that's pretty fast. But how do we figure out how far does it go in a year? And I took the liberty to put up the calculations up there. 186,000 miles in a second times 60 seconds times 60 minutes times 24 hours times 365 days. And oh my goodness, look at that. 5,865,696. It's just 865,696,000,000 miles. So that's a mouthful, and that's only in 1 year. And if you think about it, when you talk about the nearest stars, if we're going to round this off, we're going to call 5.9 trillion miles per year that light travels. The nearest star is Proxima Centauri, so that means it's 4.24 light years away, and we're already at an astounding 25 trillion miles. So when you start talking about the Andromeda Galaxy being one of the largest of the local group of galaxies, it's 2.5 million light years away. And you can see that with your unaided eye. And it's incredible when you think about that. If you figure out the number of zeros that this pulls in, and that's one of the closest galaxies, you can see why astronomers convert over to the nomenclature of light years. So what is it all about? Webb had to be designed to image the universe deeply and powerfully. Now that's easy to say, but what does it mean? It has to meet 4 main criteria. First thing is you have to go into space. You eliminate the interference and turbulence from our atmosphere, and you have to go to a place in space where you're shielded from the heat energy output of the Earth. Believe it or not, the Earth has a lot of light reflected off it, the sun, as well as the moon. So we picked the Lagrange point. Lagrange point, very simply, is a point in every object in the solar system has Lagrange points. There's 5 of them, and they're points of gravitational balance. So there's a Lagrange point L4 and L5 where things go before the Earth or preceding the Earth in orbit around the sun. And objects that go there will just remain stationary without the need of extra fuel to be there in orbit. Picking Lagrange point 2 goes beyond the orbit of the moon, approximately 1 million miles from Earth. But the additional thing that's important about L2 is we're now shielded from the sun, we're shielded from the Earth, and we're mostly shielded from the sun reflecting off the moon. So everything that comes to focus on the mirror has to be gathered and put onto the onboard instruments that are on board. And this is going to be important to understand this is an infrared telescope. So it's not a visual telescope like Hubble. So infrared is important because everything in the universe is shifted to the infrared as we move away and look at deep space objects. Those objects are basically shifted at high speeds of light away from, seemingly away from us. Hold on a moment. So this was decided to coat it with gold so we could reflect the maximum amount of infrared energy. The gold basically is 100% reflected of infrared energy, and that's important to understand that. And that's one of the most important parts of the telescope. When a person looks at the telescope for the first time and sees these gold reflecting mirrors, there's a total of 18 of them. That's important to understand that because it's 6.5 meters across. It's got 18 hexagonal mirrors, each 4.3 feet across. And the reason for each of these mirrors is you have to fold this telescope as much as possible, like origami style, to place it inside the largest fairing on the largest rocket that was available. And that's ESA Ariane 5 rocket. And of course, it must be sensitive to the wavelengths needed to see deep into space, infrared. This gives you a sample of what we're talking about. The Hubble primary mirror was 2.4 meters across. The James Webb Space Telescope mirror is 6.5 meters across. So it is really huge. But the important part about infrared is now you have to introduce some kind of shielding, because even though you're in space, and yes, it is cold up there, trust me, it is 355 degrees below zero. Not cold enough for everything that James Webb has to do, because it's an infrared telescope. Any amount of heat energy that impacts, that distracts from a target that we're looking at almost to the beginning of time, right after the Big Bang occurred. There's your Lagrange points, and you can see the one we want to get to is the one well beyond the orbit of the moon, and that's L2. And that's going to take about 30 days to get there. And that, although it's not perfectly ideal because you still need a little energy to remain in place in that Lagrange point, it shields, it answers the other problems we have in an infrared telescope. It's got to be perfectly shielded from the sun, reflected light off the Earth and the moon, and that's the place you have to go to. And here's what we're talking about. This is the electromagnetic spectrum, and everyone is so familiar with visible light, all these beautiful images that Hubble has downloaded. Hubble in itself has a slight capability in the ultraviolet and a slight capability in the infrared, but not what we need to see through the very beginning of the birth of the first stars and the birth of the first galaxies. And that's what James Webb will do. So you can see the extended range in nanometers that the James Webb will bring to it. It still does a little bit of visible, but it's mostly in the orange and deep red. So you're not going to get any beautiful visual pictures, but trust me, the images coming off the cameras from the James Webb will be spectacular. And here it is. This is what I'm describing. Two sides of the Webb Space Telescope. And you think space is cold. When it comes to James Webb, not quite cold enough. So the hot side, 185 Fahrenheit. So we have a 5-layer set of panels that have to be eventually unfolded on the way to L2. There's 5 layers of them. They got to gradually acclimate, because you got to understand, when we're going from a water-rich planet and a nice, comfy, warm planet, and we're going into deep space, and all of a sudden the temperature drops well below zero, and you got to dissipate all this water. Anything you do in the way of tensioning the fabric on anything that has to be unfolded, because it had to be folded to fit inside the rocket fairing, has got to be done gradually and with precise signals being sent up, so the spacecraft does not tear or pull anything apart. By the way, these 5-layer deep solar panels, they're made out of polyimide. They're coated like a mylar piece. I guess a lot of people are familiar with mylar, those mylar blankets that keep people warm in the cold of the outdoors. That is about the size of a tennis court. So that gives you a size of the dimensions we're talking about. The cold side is 388 degrees below zero. There is one instrument on board. You think that's called 388 below zero. There's one instrument on board called MIRI that has its own cryogenic liquid that drops it to a further 454 Fahrenheit, almost absolute zero, because of the sensitivity of its instruments. So here are the key elements to the James Webb Space Telescope. This is what it looks like. Really spectacular. Like I said, the first thing you notice in any pictures of James Webb is that gold mirror and the 18 hexagonal segments here. So the OTE describes everything to do with the optics. And that includes the tertiary mirrors, the secondary mirrors, and all the mirrors that are basically working to stabilize the images as they're distributed to the onboard instrumentation. Multi-layers, okay? Sun shield. And then star trackers, you got to keep on track by million, the amount of flexure that is allowed on those mirrors to bring them into focus is like, you're talking millions of an inch. So it's really precise. And the spacecraft has a lot of electronics in it. So the bus is very important to send the signals to all the instruments to work and function properly and to make sure everything is deployed after launch going into the L2 position, which is going to take about 30 days from launch till it reaches the L2 position beyond the moon. That's very essential to downlink the data to the deep space network with an Earth pointing antenna. And then we, of course, the first thing that's going to do before it does anything else is when it's in orbit, you got to make sure those batteries are charged. So you get your solar power array, which is unfolded, and you make sure everything is charging properly before giving it any further commands. And a lot of people think this is unusual, but if you see there's a trim flap in the picture that everyone's looking at, that trim flap acts like a steering mechanism for correcting for a bit of angular momentum, a little bit of swing that is caused simply because you've got this massive object, which is hurled into space toward the L2 range, and it's just going to continue moving in that direction because of Newton's laws of motion basically gave them a push, and it's going to keep moving until something stops it. And the thing that's going to stop it is L2. But along the way, there's a lot of mass there, and you have a little bit of flexure in the spacecraft, and that's what the trim flap helps to dissipate and stabilize the whole spacecraft. And then, of course, well behind the instrumentation mirror that you see right up front is the science instrumentation module, which controls everything and allows scientists to tell what instruments should be turned on. Yeah, I got to put this up there. I don't want anyone to get scared and start dropping off here. But this here is the MIRI light path. So like I said, there's multiple mirrors which take out, it's almost like image stabilization. If you got a brand new camera with image detectors basically in there, they really do an amazing job. I've actually taken pictures of the stars and planets at night by hand holding my camera. So that's how good image stabilization is. Image stabilization is essential for James Webb. And you take all the flexure and all the wobbling and all the jostling that goes on board this giant telescope. And here's what you have to do to build it. This is one hexagonal mirror. Everything is done in a clean room that it's cleaner than a hospital operating room. This is what I did for about 35 years. I wore a mask on the inside, and then I wore a full bunny suit with a mask on the outside. So I was double masked. The full time I was in a clean room, much like these people were. And you got to think about this. You're in a full bunny suit. You've got gloves on, usually a double set of gloves. You have ESD wrist straps. And when you're working on the mirror, everything is strapped into you, so you can't drop anything. Nothing worse than dropping something on a $10 billion telescope with its very fragile mirror. So that's very essential to understand. A lot of these people dedicated their life to getting this telescope up and running from about 2006 going forward. And here's one of the tertiary mirror, which means it's the secondary mirror. that allows you to relay the information to the instruments out back. And this is the head of Ball Aerospace, which worked a lot of these mirrors and make sure everything is perfectly aligned, along with the coating company. You had to coat each of these mirrors, and the larger hexagonal segments, there's a total of 48 grams of gold, which is not a lot of gold. So we're talking about fractional amounts of gold, but just enough to make sure you reflect 100% of the infrared energy hitting the mirror. And all these other mirrors have to relay this down to the instruments. So once you get behind the mirror, this, I kind of geek out over this. I hope other people will appreciate this. This is the structure needed to ensure there is no flexure in bringing in the focus. When you're removing an object that you spent the last 20 years building on a planet called Earth, which is full of water, nice and warm. Now you're going to space with these extreme temperatures. The only thing that would put up to those extreme temperatures and not add too much flexure to it is beryllium. So that whole frame structure, including the mirrors, they're not made out of glass. They're made out of the material called beryllium. And you can see the example, what is behind each of these beryllium mirror segments. This is just a model of one. So you have the beryllium substrate coated with gold on the front side, and you have all this instrumentation with the electronics box below. And you have to actuate these sensors that allow you to kind of bring each of the mirror segments to contribute to total focus across the 18 hexagonal segments of this mirror. It really is state-of-the-art technology. And all this is due to the fact you got to fold it up and put it in this fairing on top of this giant rocket, which is going to be taking off from the ESA launch space of French Guiana in South America. And look at this, find focus and image by shifting them 1/10,000th the diameter of a human hair. Just think about that. That's a challenge in itself. And then you say, okay, by the way, we're going to do this at 388 below zero. So it really says, I want to challenge you beyond human comprehension. So it's also a telescope meant for wide field imaging. So whereas telescopes like Hubble go deep field, we want to wide field image it and get as many galaxies and analyze these as thoroughly as possible using this infrared mirror. So you can see this is one of those diagrams I just put up there. There's a Cassegrain focus up here, which means you have a combination of mirrors and lenses that allow you to kind of steer the light path to the back where you have the focal surface, and it's distributed to the various instruments. And of course, everything is steered by a series of small steering telescopes that allow to make sure that you are correctly looking at the target you want to look at. And the other thing is, if you're looking at a bright object like a galaxy with a bright core, or you're looking at nearby stars that are overwhelming any exoplanets you might want to look at, you have to use some of these, what they call coronagraphs. And if I use the name, all a coronagraph means is it's a disk that blocks off the light of an object that's a little too bright. It is so bright, it would overwhelm the instruments from seeing the moon or seeing the outer parts of the galaxy, like the galactic spiral outer arms. And that's important to understand that. And a lot of that is done electronically through using of filters. Instruments. There's 4 main instruments. Here's the first one. This is called NearSpec, which is Near-Infrared Spectrograph. And it can view, and here's the exciting thing. I used to work in a lab down in Shrewsbury, and we came up with a technology that does micro shutters. And it allows you to open and shut shutters that are microns across. So very tiny, to give you an example, human hair diameter is about 75 microns across. So I'm talking about something that's a micron across. And this allows this telescope to view as many as 100 galaxies or 100 different stars at the same time. Whereas Hubble would look at one, move to another, look at that one, move to another. This one could look at 100 objects at the same time. And as the telescope got built over a 20-year span, you can see where the pilot array all the way on the left, was what they first came out in the way of micro shutters. What they actually put on the telescope is in the middle. And of course, hey, technology marches on. Look at what they've came up recently. But unfortunately, you have to go with what you have. And the telescope has this 365 by 172 array. But the nice thing about it is there's 4 of them. So there's more than enough to basically allow James Webb to do state-of-the-art observing. So we're going to star watching technology with thousands of these micro shutters. And to give you an example, this is what each of these micro shutters, and there's 4 sets of these. And you can see how tiny these are. And like I said, they're micron size, so they're really tiny. I'm going to just give you a sense. I found this on the European Space Agency website. How does the light actually enter this spectrograph? There's no sound other than the initial sound. This is a diagram, a CAD diagram of the actual inside workings of the spectrograph. But I thought it was fascinating because it portrays how we parse the individual light beams coming into the telescope and put it through to the various instruments. So there's your light beam. The first light beam is accepted by this mirror, which is bounced off an internal mirror, which is bounced off another mirror, which then goes through secondary mirrors, which then goes through filters, which then gets distributed to other instruments and other filters. That might be prisms. They may be grisms, which are prisms that are ruled glass prisms. And they analyze the light in the spectrum needed for figuring out what they are actually looking at. So you use the spectrograph to determine exactly what is happening in distant stars, distant galaxies, or maybe the atmosphere of distant exoplanets. So here's MIRI, and MIRI is the instrument that was on board, basically, that I mentioned, has its own cryo coolant. So yeah, 388 degrees below zero, that seems cold to us, but MIRI is so sensitive that it requires even a lower temperature. So it's almost approaching absolute zero. So it has its own liquid helium cryogenic material on board to keep it as cold as possible. And this is an international collaboration from Germany, France. This is Rutherford Lab in England. We have the Canadians involved in that. The Europeans are contributing the launch vehicle. So it's international collaboration. And once again, I kind of relive every time I see these workers inside a lab. That's what I look at for most of my work career over 35 years in labs throughout New England. And you can see there's a wrap put around all these instruments inside because you have to basically maintain a really critical temperature across the instrument to make sure it is cooled to almost absolute zero. So that's how you do it, by putting these wraps on board. And MIRI stands for mid-infrared instrument here. But the thermal shield is tested. By the way, all these things had to be put inside vacuum chambers here on Earth. They had to be rigorously tested at temperatures that they would see in space to make sure nothing broke. And then after telling people, be careful and how you manage or handle everything in space, they had to inform people they're going on a shake table that would shake the heck out of these instruments. And many times things broke, solder joints busted, and they repaired them. They shook them again and again and again until eventually nothing broke. So people are wondering out there, how do you actually get this to work in space if you're building it in a water-rich and a warm environment like Earth? So this detector is going to allow it to make observations of distant galaxies, newly formed stars. And we're talking about the stars that are just turning on at the beginning of time. How do they come to form galaxies? Did the stars collect together and by their mass form galaxies that were much larger? Or did galaxies form out of collapsing clouds of gas and then stars started appearing along the many spiral arms of the galaxy? No one knows. So this is what we're seeking to answer, as well as looking in our own solar system at planets, comets, and the disk debris in the Kuiper belt. So this is very important. And here's just a simple graphic, which I thought was very eloquent in the way it shows you Everything, as we look out, there's no favorite position in space. So whether I'm in the Andromeda Galaxy, the Milky Way Galaxy, everyone sees the same thing we're seeing. Everything seems to be moving away from us. So as it's moving away, everything shifts to the red. So everything coming to our eyes is in the red. If things approach us, they look blue. Now, how can we make use of this? Guess what? If you're looking at a galaxy and it has some rotational portion of its speed away from us, you might see some light on one edge, blue, and some light on the other edge, red. Well, the red light means it's going away from you. The blue means it's coming toward you. That means you're analyzing the rotational velocity of that massive galaxy. So you can tell a lot from spectrographic analysis and the camera analysis in the infrared. And this is the NearCam camera, which is going to be basically the prime instrument for investigating. Once again, I got to hand it to these guys. These guys spend 10 to 12 hours a day suited up in these bunny suits. They have everything attached to themselves. I've seen these guys on these platforms on their bellies, reaching out, doing work with soldering instruments and attaching bolts and nuts. And you got to make sure you're very careful on that. But just imagine laying on your belly in these uncomfortable suits for 8 to 10 hours. It's a lot of work. And these guys were dedicated to doing this and make sure we got off it, even in the middle of a pandemic. But you can see they were dressed for it basically and being isolated within the confines of the clean room. So this is taken right here in Greenbelt, Maryland, basically. So that's what the instrument looks like. NearCam is the primary imager. You got to know what it takes. So on the right-hand image, that's Hubble. In visual, on the left-hand image, this is an infrared image taken by Hubble. Now, Hubble has a very limited capability of resolving things in the infrared, but just gives you a hint of what we're talking about infrared. You can clearly see on the image on the right, this is something we call the Horsehead Nebula. Reminds people of a horse's head. You can see a bright spot on the upper brow of the horse's head. What is that? No one knows. Well, in infrared, you're starting to poke through, you can find a brand new star forming in that region. And as you look deeper into it with Spitzer, this is not a Spitzer image, you can also see there is solar system debris like asteroid belt, comet belts, and things of this nature. So this is the importance of an infrared telescope. It will not allow the dark molecular clouds to block our view of finding out how our universe came to be and how it functions. So here's the fully assembled instrument rack. This, by the way, is the last instrument. This is the near-infrared instrument and slitless spectrograph, NIRIS, on the bottom, and then the fine guider sensor, which is on top. So the combination of these 4 instruments are put together in a rack, and of course, every spacecraft that goes into orbit has a patch, and this is the patch for the FGS and NIRIS. And we have a patch for the overall mission. And this is the way it's configured here. So this is a layout of all 4 instruments. So it's a pretty tight space. Everything has got to be functional. So you say, what do we get for $10 billion? You get a lot of state-of-the-art compact instrumentation that have to function at this extreme range in space. And guess what? It's got to put up with almost 40 Gs of vibration for this giant rocket launching it into space. So there's a lot of trauma going into space. And then once you get there, the other trauma is just cooling down to the ambient temperature of space before you actually can function. And these are these filter wheels. I just wanted people to have a closer up look. We use the term grisms. Grisms are just prisms that are glass. They're ruled, basically. And by ruled, I mean, you might have a 40, 50, 60,000 rulings per inch across this glass. So it really allows you to parse the wavelengths of whatever light is coming in here to the wavelength needed to determine what is going on at the very beginning of the start of our universe. It made it. Now, this took 20 years of effort, okay, of construction to get it to this point. And then, of course, everyone is still functioning with the quarantine we're going through, COVID-19, they continued working through because they were announced, designated as basically workers, basically that needed to do an important job. So they were designated as essential workers. Of course, everyone was in a clean room lab and under isolation anyway. You put all this together, it's $10 billion. You want to make sure it gets there. And guess what? Threats from pirates. I mean, you cannot make these things up. There was word that pirates were going to capture the ship and hold the James Webb Space Telescope for ransom. I mean, I heard this and I thought, someone's making this up. Please say someone's making this up. This can't really be happening. Yes, it happened. NASA took hold of this along with the military. And as you can see, it made its 1,500-mile journey in this innocuous, basically, it doesn't look like much of anything in the way of a ship called the Colibri. And it made it there successfully, probably under guard or escort all the way down. And this is its clean room. Everything is done in a clean room. So you ship it down to the launch port from basically the West Coast, and basically you put it inside this huge clean room chamber. And then they open it up and you can see how large this is. If people can see right at the bottom, the fact you have some of those people in the bunny suits at the bottom are about 6'4", and you can see how large this telescope is by just telling you the sun shield alone is about once it stretches out, about the size of a tennis court. So this is very large. And you can see it's now in its vertical configuration. And this is exactly what it's going to look like when it's put inside the Ariane 5 rocket fairing at liftoff. And there's the Ariane 5 at liftoff right there on the edge. And you can kind of clearly see where it's located, basically folded up inside origami style. Now, I think it's important talking about getting it to this point. 20 years worth of effort. Don't touch it. Don't drop anything. Don't do any damage. Make sure you shake and bake it. Make sure you make sure that absolutely everything has been thought of so it succeeds in getting launched into space. But hey, did anyone mention I've got to sit it on top of a rocket, and it's got to undergo the launch into space and then take 30 days to arrive at L2. Here is what's going to happen at French Guiana ESA Spaceport. Here's what it looks like inside the fairing. The main rocket engine starts first, much like the shuttle did, but there's only one main engine, and then the outboards, the solids light. And once those solids light, that's most of the energy of the rocket to get it well above 40 miles of the Earth's atmosphere, and then the main rocket carries it the rest of the way into orbit. Like I said, there's a lot of shaking going on here. But this is the European contribution. They said, we will provide the launch vehicle with this enormous fairing free of charge. That's our part of the contribution, in addition to doing some other optics work as a contribution to the international effort to launch this James Webb Space Telescope. About 30 miles high, there you are, and there's the fairing. Initially, there was some work concerns. They had to do some testing on the fairings because you see there are explosive bolts that have to push that fairing apart, and there was some concerns they may be too extreme and cause some tears in the sun shield. So they had to do some adjustments to that. They had at least 10 flights before this flight, which is going to occur on December 18th, to make sure the fairing problem was fixed, and it has been fixed, according to NASA. So they're ready for launch, and it is ready to go. But this is what it's going to look like in low Earth orbit. And it just gives it a boost to L2. And people say, how is it propelled? It just, Newton's law, give it a push. And unless any outside forces act upon it, it is going to continue moving in the direction of L2. And there's the spent rocket motor. There are certain engines on board that will allow you to make fine adjustments, but they're not huge rocket engines. And this is it unfolding in space. Beautiful classical music theme. I love the Europeans, but this is appropriate for this wonderful, beautiful telescope that has to pirouette and make slight adjustments to make sure it is unbelievably successful at the very start. There's like thousands of things that have to go right, and all these nuts and bolts have got to work. And you can see the sunshade has been displayed, uncovered. You have the secondary mirror there, and the basically two segments on either side. There's the left segment, right segment are kind of folded in to make the complete hexagonal mirror of 6.5 meters. And that's what it's going to look like once it gets to L2. And then there will be a further, it still will not be cold enough to do observational work. So they want to make sure all the moisture is removed. Basically, it gets cold and cooled down. And they do some testing to make sure everything was successful. And every bit of the way, by the way, when you see this, it doesn't unfold within a matter of 5 minutes like it shows in film. This takes part over a 30-day span. So if they send a signal to an actuator, let's say for deploying the sun shield, and there's some pullback on an actuator, they hold. And they kind of analyze what is the problem and what do they need to do. So they might go back and forth between the left and right portion of the sun shield to make sure it's fully deployed. You got to understand, this has been folded up inside the rocket over a period of time, plus it's been folded up before then, and it may take a little bit of coaxing to get it deployed in the vacuum of space, but that's what it's made for. And this rocket, like they said, 95% success rate. And boy, this is the most evaluated rocket in the history of mankind with a $10 billion payload going on it. So here's the 4 main science themes we're going to get involved. And I talked to NASA officials, and they indicated it's already booked for the first year. So 1 year worth of observational programs are already booked solid. Hubble is lining up candidates for what it should look at, what it can't resolve by its own, and what we need a telescope like this to do. So at the first light, when did the first stars turn on? And slightly after that, we're hoping to get a look at these giant stars. Typical stars, the largest stars in our universe may be anywhere from 50 to 80 solar masses. These are massive stars. They may be 300 or more solar masses at the beginning of time that first formed. How did galaxies assemble? The birth of stars and protoplanetary systems. How did they start? And looking for the origins of life. And once again, you got to appreciate, these are the pillars of creation called the Eagle Nebula. This was actually, I think, in Newsweek or Time magazine. And this is an Eagle Nebula. And this you can easily see through a Aldridge telescope, but not in this kind of portrayal, but you can see it. And it's a nebulosity that has a lot of intermolecular gas that looks only impervious to our eyes in visual wavelengths because it's multiple light years across and multiple light years thick. So we're talking about almost a pure vacuum, but even a pure vacuum, when you have a few atoms of this intermolecular gas over a period of time, it builds up these dark clouds that you can't see through. And on the right, you can see what the infrared will do. And the infrared is going to be more spectacular with the Webb telescope once it comes into view, because you're talking 2.4 meters to gather this, and this is what we can see. Guess what? 6.5 meters is going to resolve in incredible detail what's going on there, how brand new solar systems are forming, how asteroid belts form, how cometary belts form, and things like that. So this is an understanding of our universe. This is a beautiful illustration. You need illustrators to kind of tell people, what are we talking about when we talk about exploring our universe? Illustrators portray something we can't see. There's something called active galactic nucleuses, these quasars pouring out tons and tons of energy from its central core. In fact, the brightness of the energy coming out from these active black holes in the center of these galaxies are so overwhelmingly bright, they thought they were stars. They couldn't even see that they were galaxies. And these are hard to define. They're going to go after something like this. Guess what? Within the last 2 to 3 weeks, Hubble released an image. Okay, so this is an illustration. This is an actual physical image of a galaxy we call a Seyfert galaxy with an active galactic nucleus. I just described, you can't see this. Why is this one being shown in such great detail? We don't know. Something is going on here with the way that galactic nucleus is activated that's allowing us to see it, even with Hubble's capability. And that's one of the prime candidates now that we're going to use. Now, the other thing, the important part about this is our Milky Way galaxy has undergone maybe 200 to 300 collisions with a lot of dwarf galaxies over its life history of 5 billion years. And it's undergoing one with a dwarf galaxy, which is shredding. So it built up its mass over a period of time. So that's what galaxies do. They collide with one another and add mass to them. So we understand how galaxies started. But better yet, how did those first galaxies started? How do you collide with something that is just being born, right? I mean, how does this work? So this here is a NGC National General Catalog 5728. And this here is a really amazing barred galaxy, much like our Milky Way, but it's got a very active core to it. Here's an example of what I described in the way of colliding galaxies. Way in our future, Andromeda is going to be coming with a near collision to the Milky Way galaxy, and will combine over a number of billions of years to form one giant elliptical galaxy eventually. But these are galaxies we can see in deep space. And this here is NGC 5954 and 5953 in the lower part. All those are designations for these galaxies, so astronomers know what they're talking about, where to look for them. And these galaxies basically spent a lot of time doing these collisions, splitting themselves apart. And stars do not die in collisions. That's the misnomer. Most people think stars are destroyed. When galaxies collide, it's the gas in the galaxy that collides. And when gas collides, you form brand new stars. Take a look at this. This is as deep as Hubble can get. And this is a deep snapshot that Hubble analyzed. And you can see each of these little square portions of the large image on the left of each of these images, enlarged on the right. And there are galaxies that are well beyond our capability because there's massive galaxies in the front. And those massive galaxies lens or bend the light because of their mass in the forefront. They're bending the light of giant galaxies that are almost at the beginning of time, 13 billion light years behind them. And they're bending the light in the forefront. You'll now have the Webb telescope able to analyze through its spectrographs what is going on with these distant galaxies and how many stars were in there and how did it come about to form. But we get hints of this. So when Hubble goes through the motions, it goes through the motions of saying, here's some prime targets. I can't quite figure out what's going on because I don't have the capability. So here's a prime candidate now for the Webb telescope to look at. This also, believe it or not, Hubble after 31 years is still producing. This is Betapictoris, and this is an easy star to look at. It's in the southern fishes, Betapictoris, with the Hubble Space Telescope. And this is what we're talking about, basically a coronagraph. The coronagraph, as you can see, the black spot in the middle, all it does is it electronically blocks off the overwhelmingly bright light of the central star from Betapictoris, and it allows Hubble to take a picture of the dust throughout this brand new baby star forming with the solar system. And they're finding comets, they're finding asteroids and icy objects and probably planets in there. So it's very important now to hand this off to Webb to get a more detailed image of this. This is a spectacular illustration of hot Jupiters, brand new exoplanets. When we went out to look at the solar systems, we said, hey, our planetary solar system is probably typical. Guess what? Rarefied. Can hardly find any that look like ours. most of them have hot Jupiters. Hot Jupiters are Jupiter mass-sized objects, 2, 3, maybe 10 times the mass of Jupiter, but they're almost touching the star they're orbiting. And they burn off a lot of this helium and hydrogen. They're contribute the contribution to the atmosphere of these Jupiters. Take a look at all the planets forming. Can you see them? This is a intergalactic molecular cloud. It is spectacular, and yes, there are planetary systems forming. So watch planets form. How do we help? Hubble. Hubble is taking images and close-ups in that area you just saw moments ago. All these planetary systems are forming by the use of the coronagraph. They can see the dust, asteroids forming, they can see planets forming, and they want Webb's capability with its 6.5 meter mirror to peer deeper and resolve it in pristine detail. So these are 17 protoplanetary disks, and this is analyzed by the sub-millimeter array at Atacama, which is ALMA, and this is now a priority during that first year of observations that they're going to do. My favorite thing that I started off as an amateur is to show people, and myself, I still love looking at it, the nearby Orion Nebula, which is a stellar nursery with brand new planetary objects forming, and these are called proplyds. So all these black spots that you can see here that don't seem quite resolved, well, we can't resolve them because we can't penetrate the dust cloud. They're forming brand new baby suns and brand new solar systems in there. So there's planets forming, there's comet belts forming, there's dust clouds forming, maybe even dwarf planets are forming in those solar systems. All these have been kind of charted out. I think they determined there's about 300 of them in the Orion nursery nearby nebula, and they're going to hand it over to James Webb to look at it in detail in the first year. Talk about Van Gogh. This is an image produced by Juno in infrared, okay? Juno is an orbiting spacecraft that for the first time went in orbit around our largest solar system planet, our gas giant called Jupiter, and we're orbiting the poles of Jupiter, which we've never done before. We've orbited around the equatorial plane. We're looking down and we're getting these stunning, you can see each of these disks here. I think there's 8 of them there. Each of those is about 700 to 800 miles across. And they're there over and over and over again as we do these deep dives. Why are they there? How do they maintain their integrity? What is going on? What is it telling us? How deep do they go? Even the red spot we want to know more about. So even though Webb is going deep space, and I'm all excited about that, hey, I love to learn more about what's going on in our own solar system, get some more clues before we launch. And just to remind everyone, L2, once that rocket, and I'll tell you, everyone in Aldridge is going to be sitting there and biting their nails after waiting for 20 years for this rocket to take off, that 8.5 to 9 minutes before it gets into orbit, it's going to be a nail biter. And then after that, it's 30 days until everything unfolds and gradually on the shakedown cruise till it gets to L2. And then L2, there's the shakedown cruise of 5 months before you actually get the first images back. And you got to do everything gradually, because like I said, you can't just throw a switch and something that used to be on a warm, moist, wet world like ours and throw it in an environment 388 degrees below zero with no moisture. You got to make sure you do this very gradually, very easy to break if you push the limits too far in some of these actuators. They're meant to survive, but you got to treat them with kids' gloves. So this is why they take their time in the deployment. So before going any further, and I'm going to entertain questions at the end of this, I did tell people and assured people that every month you have a downloadable program called What's Up, and it's NASA What's Up on YouTube, the NASA channel on YouTube. And it's What's Up for November, What's Up for December, What's Up for January 2022. And this is the What's Up for November 2021. And within 3 minutes and a few seconds, it gives you a total overview of what you can use the library telescope or any telescope you might have, or even binoculars to see up in the night sky. So I'll let this play now.
sunset planets, a partial lunar eclipse, and the return of the winter stars. From November 6th through the 11th, watch the moon glide past Venus, Saturn, and Jupiter after sunset in the south-southwest. In particular, if you step outside for a look on November 7th, you'll find the 4-day-old crescent moon just about 2 degrees away from Venus. Should be really pretty, so don't miss it. And now through early December, you'll find Jupiter and Saturn drawing a little closer to Venus each night. A partial lunar eclipse is on the way, taking place overnight on November 18th and 19th, when the moon slips into Earth's shadow for a couple of hours. Weather permitting, the eclipse will be visible from any location where the moon appears above the horizon during the eclipse. Depending on your time zone, it'll occur earlier or later in the evening for you. Now that's a huge swath of the planet that'll be able to see at least part of the eclipse, including North and South America, Eastern Asia, Australia, and the Pacific region. So check the timing of its visibility for your area. For U.S. East Coast observers, the partial eclipse begins a little after 2 a.m., reaching its maximum at 4 in the morning. For observers on the West Coast, that translates to beginning just after 11 p.m. with a maximum at 1 a.m. Partial lunar eclipses might not be quite as spectacular as total lunar eclipses, where the moon is completely covered in Earth's shadow, but they occur more frequently. That just means more opportunities to witness little changes in our solar system that sometimes occur right before our eyes. All month long, if you're up late and cast your gaze toward the east, you'll notice some familiar companions have begun rising late in the night. Familiar stars of northern winter skies are returning, rising late at night and sitting high in the south by dawn. By the Pleiades star cluster leading the constellations Taurus, the Bull, and the Hunter, Orion, followed by the brightest star in the sky, Sirius, all of them back to keep us company on the long winter nights here in the northern hemisphere. And for those in the southern hemisphere, they're keeping you company on shorter nights as spring gives way to summer there. A fun note about the Pleiades this month is that several of the 8 asteroids to be visited by NASA's Lucy mission are located in that part of the sky. The Lucy spacecraft launched on October 16th on its 12-year mission to visit a bunch of special asteroids called the Trojans. They share the orbit of Jupiter, with a group of them leading the planet and another group following behind it. Lucy will be the first space mission to explore this unique group of asteroids, providing new insights about the formation and early history of our solar system. Here are the phases of the moon for November. You can catch up on all of NASA's missions to explore the solar system and beyond at nasa.gov. I'm Preston Dykes from NASA's Jet Propulsion Laboratory, and that's what's up for this month.
This is pretty straightforward, easy to understand, and it gives you a sense of what's going on in our solar system and what you can observe if you took out the library telescope. One of my favorite things is just to grab a pair of binoculars and take them outside and just look at the Orion Nebula. Before I open up to questions here, NASA, for everything it's done over its whole history, including going to the moon or any major bits of exploration, and I'll tell you, working on this Webb Space Telescope, this is a major event equivalent to the technology that had to be developed at the time for going to the moon. So a lot of these technology had to be created to make it work. They invited 21 artists all across the globe to participate, and you can see some of the results. And of course, a lot of the things that are featured in these artworks are the mirror. That gold mirror is just prominent. And you got posters that are made. They even had 3-dimensional sculptures. So this is really unbelievably amazing. And to get the kids involved and even some adults who might be interesting, they have a game they put online on their website for the James Webb Space Telescope, and it's called Scope It Out. So they make comparisons between the James Webb Space Telescope and Hubble and your backyard telescope, which you can take out from a library, which is a tabletop. This one is probably be a 6-inch reflector that you put on a tripod. But either way, it's kind of fun making comparisons. One of the things I find interesting is the technology has improved so much, and the fact that we're making the mirrors on James Webb out of beryllium, and it's as lightweight as possible because of the honeycomb structure. James Webb, which is larger than Hubble, actually weighs less than the Hubble Space Telescope with its smaller mirror. And that's simply because the technology over a period of time has allowed us to do it with lighter weight material. So without further ado, I guess I'm going to stop, open myself up for any questions. Let me just
Okay,
see.
we got one here, Jim. I'm going to allow them to ask the question. Carl and Elise, you got a question? You can unmute and ask it.
Yeah, go for it. Do I have to click?
Well, I just asked them to unmute.
Okay. Okay, there they go.
That wasn't us.
We can hear you, Carl. Go ahead with your question.
We didn't have a question.
Oh, well, we raised your hand, so I thought you might.
Oh, it was a mistake.
Oh, good to hear your voice.
Yeah, it's good to hear from you. It looks like we had about 24 max participants, so I appreciate everyone coming out and giving me some time. We did a couple of these talks recently indoors, and I think you guys are smart doing what you're doing, because most of the indoor talks were in large rooms with a lot of ventilation going on. We all had to wear masks indoors, but we got 13, 14 people indoors. The one recent event I did last Friday, where I mentioned once again the James Webb Space Telescope, in addition to everything else going on in the night sky, and showing them Jupiter and Saturn and Venus, we had 45 people turn up. So I guess I'm starting to learn in quarantine times, and where people are a little nervous about going inside, indoors, basically the best thing to do is to have an outdoor stargazing party. And it's quite amazing to have it turn out like that. And I'll tell you, we had tons and tons of questions from people who are very eager to look through our telescopes, plus ask about James Webb. So we really appreciate that. And we appreciate what you guys are doing here through this Zoom meeting. So thank you.
All right, just so everybody knows, we will be sending out an email tomorrow that'll have a recording of this talk, and will include the webpage for the Aldridge Astronomy Group. And if you have further questions, I'm sure Jim would be happy to receive them.
Yes, please post it online. I assume you have an online site where they can ask some questions, and I'll check in there and answer any questions you upload directly, or you can forward the questions off to me and I'll answer them all.
Jim, I have a question
Yes.
for you.
Go for it.
You mentioned the ability to image exoplanets. I've heard that the ability to detect water on rocky exoplanets is something that NASA is very interested in. Will the James Webb Telescope be able to detect water on exoplanets?
Yes, it will be able to. One of the things that is kind of humorous, but it shows you the power of James Webb. They'll actually be able to do weather forecasting on some of the nearby exoplanets. What kind of winds are going on the exoplanets? What is the composition of the clouds on the exoplanets? Does it have a solid rocky surface? Is it waterborne? Things of this nature. And when I'm saying nearby exoplanets, I'm saying 2,000 to 3,000 light years away. So nearby. But that's amazing that we could reach that far into space and know the level of detail that we have right currently now. We just had a breakthrough, and I'm trying to think how it was done. And I apologize, I can't remember the specifics, but it just came up on the internet within the last 24 hours, where they found the first exoplanet in another galaxy. And you think about finding something that is hidden by starlight within 3,000 to 4,000 light years of Earth in our galaxy, and then you're finding out we found a exosolar planet in a distant galaxy. That's amazing. And by the way, it wasn't Andromeda, which is nearby. It was something like in a galaxy like 20 million light years away. So it's pretty far away. And it was amazing how they came up with that finding. But yes, we will be looking for water vapor, specifically oxygen, methane, things of this nature in the atmosphere that will give any hints for any kind of biological origin associated with that.
Okay, Jim, I got two questions.
Go for it.
One is the video you showed at the end on nasa.gov. But where do you find that? With What's Up November?
Yeah, I'll tell you what, Dave. What I'll do is after this meeting's over, I'll forward you the link so you
Yeah.
can get it very easily, and then you can post it for your everyone in your group that basically access it. I like it because once a month, and make sure you do not what I did when I first started out doing these programs. I went in, what's up for November or what's up for December, and I didn't put NASA, and I got every kind of basically music group going for what's up. So you got to make sure you put NASA in there. NASA, what's up for November, what's up for December, and it really does a really amazing job. But I will send you that link that you can
Yeah,
post.
very good. Yeah.
Yeah,
If
it's
there
really
anything
nice
else,
to
there
share
should
it.
be any other links that would be appropriate.
I've got more than a few, and
Yeah.
I will forward that off to you. One thing I do want to mention, and I apologize for forgetting about this. You talk about library telescopes, and the Athol Library does have one. And if you have binoculars, this is perfect for that. Somewhere in mid-December, there's going to be a comet called Comet Leonard, was found by a person by the name of Leonard. And it may be bright enough to see with the unaided eye or with a small set of binoculars. And my unaided eye, I'm going to say third magnitude, second magnitude. So it's going to be, you know, as bright as some of the dimmer stars. But it's a very diffuse object. But it's very exciting for us at Aldridge because we always look forward to any kind of cometary object that is going to visit the inner solar system where we can look through and show people through our telescope. And that would be a fine object to see through the wide field view of a tabletop telescope that the Athol Library does have.
Very good. Yeah, another question was asking that the telescope looks like it looks sideways. Can it tilt up and down also? So it's
Yes, you have reaction wheels, basically, which are high speed, basically, I'm trying to come up with the right term, but they call them reaction wheels. And they're like gyroscopes, basically. They prevent you from using excess amounts of fuel. And just being an L2 allows you to minimize the fuel load. But every 3 weeks, you'll have to make some adjustments there. But the rest of the fine steering and moving will be adjusting these reaction wheels. So the reaction wheels will start up and spin down in various locations. And I forget how many are on the telescope that allow the telescope to slew or to move on target very precisely. And like I said, if you can adjust the mirrors to within 1/10,000th of an inch for adjustment to bring it into focus, you can imagine how accurately you have to point when you're pointing back to almost the beginning of time into a very small segment of space. But yes, it has that capability of moving itself to wherever the need is.
all right. Okay, well, gee, this has been great. It's nice that we maintained our full complement of participants to the whole event, which is always a good sign.
Yeah,
And,
thank you very much, guys, for doing that. I appreciate it.
Yeah,
Dave,
yes.
I do have a question this time.
Oh, all right.
Go for it.
This may show my physics ignorance, but when you have a telescope that's seeing these objects, how do you know that it's a solar system that's being created? How do you know that?
Oh, that is a very good question. When you're using these telescopes that are in orbit around the Earth or in deep space, in the case of Webb, what you're looking at is you're punching through an area of space that might have an intermolecular cloud, and you're finding energy of certain wavelengths that are coming back to the telescope that indicate it is a collapsing cloud of gas. Remember where I told you where red indicates it's moving away, blue indicates it's moving toward you? That can also be very helpful in determining the rotational velocity, whatever you're looking at. So if all of a sudden you're seeing a dark cloud in one band of the infrared wavelength, and then you use a longer band to penetrate through the cloud, you can figure out what is that cloud made out of, right? Is there any rotational velocity associated with the cloud? Is there a star embedded inside by the heat signature coming out? And that's where the coronagraph comes into play, because the first thing you're going to see is you're going to see something bright. And if you block it off and all of a sudden you see this darker cloud all around it that forms some kind of a shape, in the case of Orion, the Proplids, the planetary disks that are forming there. That's how they did that. They blocked off the central object, which was very bright, but still dark because it's still in the process of forming. And they found details in the outer parts of that disk. And because of the rotational velocity, they can analyze the mass of that cloud of gas and say, okay, how big is the star that is forming? Does it have any planets associated with it? And things of this. They can even estimate the age. So there's a lot of information locked into starlight. You and I would appreciate just looking at objects and saying, God, that is just gorgeous beyond all belief. Looking at the Orion Nebula, scientists basically look at it and say, man, wouldn't it be spectacular to find solar systems forming that are similar to the solar system we live in, and how that actually happened, because we're maybe at the birth of some of these solar systems. And we actually found hundreds of them just in the process of forming. So I hope that answers your question. Yep.
Good. Yeah, I had another one here that, so you did mention it's going to take several months for the array to get fully operational. But how long after the first raw data reaches NASA will results be available? Like, what are they going to, how soon are they going to get stuff?
Yeah, what they're saying, the shakedown cruise, and well, I don't want to say shakedown, but yeah, the cruise to L2, once you get to L2, you're doing it within 30 days. So then you're making the final adjustments to absolute zero, as cold as you can get. And you start gradually using the actuators to bring everything into focus gradually, like I said. So let's say January, February, March, April, May of next year, going into June, you might have the preliminary test image, quote unquote, test image released to the public, okay, to show what they found and how accurate the focus is. And then the first actual raw data that scientists would basically line up and queue up for and fight over trying to get the data in their hands, probably this time next year in 2022. So it's simply because of the type of telescope it is and the length of time it takes for it to cool down. And we use the word at Aldridge, when we go outdoors, we acclimate to the outdoors. So you want to get your telescope cooled down to how cold it is outside. That works for Earth-based telescopes too. But you also want to acclimate your eyes. So you basically get away from any stray lighting so you can see better with your night vision. Same thing with James Webb. You're acclimating the mirrors, you're acclimating the optics, you're acclimating how do we adjust that steering flap. So you reduce the amount of vibrations that are communicated in by the nature of the telescope. Its mass allows it to rock back and forth. How do we minimize that so we get the most sharpest and most accurate images possible? But I'm going to say the first initial release image, just the test image, will be probably June of next year, May, June of next year. And then this time, November, December of next year, you'll get the first loaded with data, the ones astronomers are queued up for.
All right.
I know I'm chomping at the bit. I want to look at it way before then, but I'm trying to be patient. But we all tell ourselves 20 years in the making, what's another couple months?
Okay, so how long does it take for an instruction from Earth to reach the telescope after it's in place?
That's a good question, because a lot of our space probes go to the outer part of the solar system, and we make the term in terms of upload. Like when we went to Pluto, New Horizons, it took 4 hours, 24 minutes, and 4 seconds to get a relay message down there, and the same amount to return it. Going to the moon has the advantage of it's one of our closest objects in space, and even though we're 1 million miles, so we're well beyond the moon, moon is being about 240,000 miles away, we're talking approximately 1 1/3 seconds to 2 second lag time. So we're really very quick relative to the dimensions of what we're talking about on our solar system. So yes, the communication will be very quick, very easy to upload the data, very easy to downlink the data, although it won't be downlinking consistently. It will be putting it on a drive, accumulating the data, and then downlinking it at certain points. Because obviously one of the things that's important to understand in the James Webb is you're shielding yourself. So you don't want to see the Earth. You don't want to see the sun. You don't want to see the moon, any kind of reflected light off of that. So you want to make sure you shield yourself off. And there's certain points in its orbit where it will turn the antenna and then beam what it has accumulated down to Earth. And then that would be relayed through the Science Technology Institute, which is in Maryland, Goddard, Maryland, and that will be distributed worldwide. But that is a good question, because like so many people, I hear about a spacecraft exploring the solar system and like anywhere from 1 hour lag time to 4 hour lag time or even more for some of our spacecraft. We won't have that situation with James Webb, which is kind of nice.
Yeah, very good.
Awesome.
I think we're caught up with questions. So again, I want to thank Jim for a great presentation, and we look forward to seeing what we come up with our next adventure, and hopefully we'll be in good shape. And certainly, everybody, I'll be emailing you whatever we can by tomorrow afternoon.
Yes,
So,
and I will send you that link for the what's up for November.
yeah.
And once again, I do appreciate what you've done, allowing Aldridge to give this talk. And hopefully, somewhere in 2022, we're going to link up and actually do an outdoor stargazing event, maybe an indoor
I'm
talk
all
with your
for
brand
it.
new projector.
Yeah, sounds
So,
good to
thank you.
me. All righty. Okay, well, that's it for everybody, and we